Welcome back. So we've entered a new part of the course. I already gave an introduction, which we called Life is Defiance or Life as Defiance. I think we could adopt either of those points of view. And now, today, I want to get a little bit more concrete about this by making the claim that in order to understand defiance, we first have to understand compliance. So what I want to do in this section of the course is I want to really draw the contrast between inorganic matter and living matter, and between equilibrium and non-equilibrium. And I'm going to be excited about equilibrium. I think it's one of the most beautiful ideas that has been thought of by human mind. And we already talked about the role of Gibbs in articulating that. And I've got no complaints there. But I do want to say that there are situations clearly in which we will not be able to use those ideas. But at any rate, in order to understand what we mean by breaking detailed balance, by the ways that active matter sort of defies the edicts that come from equilibrium, we need to first understand what equilibrium is trying to tell us. So you'll recall that last time I made the remark that the way that we're going to think about equilibrium is the result of removing a constraint on a system. So I'm gonna formalize this during this vignette. So first, I'm going to give you a qualitative introduction. It's still at the level of scratch and sniff, still at the level of kind of knowing about as opposed to knowing, and then I'm going to try to implement. So the picture here shows you an isolated world. This blue region is an isolated world, and I explained last time that means that this world is cut off from the rest of the universe by rigid walls, by adiabatic walls, by impermeable walls, meaning that there's no energy or mass transfer, nor the ability to do work by changing the volume or the shape of the system. And what we imagine is that there is initially some partition between the two sides, and now what we're going to do is we're going to release a constraint. So this is often a very convenient way for us to think about what's going on with equilibrium, is that we release a constraint and then we ask what happens to the system after that constraint is released. In this case, what will happen is the wheels will allow this thing to glide in a frictionless fashion. We're not going to worry about the friction issue at the moment. And it will move until the pressure on the two sides is equal. That's what we know going in. We know a priori, that's our sense of intuition, that's our sense of mechanical equilibrium. And what I want to say, which I think is glorious, is that a reinterpretation of that notion of mechanical equilibrium is that what we're doing is we're finding the entropy maximizer. We're trying to find the circumstance, or I should say the coordinate, for the partition such that the entropy of the net universe of those two sides is maximized. And that's what's shown in green here. Of course, for me to have this discussion, I need to stop talking about entropy so casually, and I need to give it a little bit more precision. So entropy is interesting, and the reason I say that is that I have this strange feeling that somehow that when we learn physics, we have this sense that energy is sort of a natural idea, and we have a sense of what it means and so on. And then with respect to entropy, it seems very complicated and tricky, especially when you do integrals over dq over t and things like that. And the thing I guess I want to argue is that, in fact, I don't think we understand it, or I don't understand energy so well, but I have a reasonably good sense of what's going on with entropy in the second law of thermodynamics. And the thing that I would want to say about it is that the second law of thermodynamics is a statement that it's almost silly in its triviality, if you'll let me use that word, which is if you set up a system in some state, it will change until it reaches the most probable state. And when I say most probable, what I mean is the state that can happen in the most ways. Now let me be concrete by using the gas molecules in the room where I'm sitting. If I take all the molecules and I put them on one side of the room, the probability of that event is 1/2. The probability of putting a given molecule on 1/2 of the room is 1/2. But to put them all on one side of the room is 1/2, which is the probability of one of them, to the power n, where n is the total number of molecules. So it becomes vanishingly improbable as the number of molecules increases. And so if I set up my system such that I had a partition, going back to this notion of the partitioning, and then I remove the partition, what would happen is that the molecules would rush over to the other side and fill it up. And the reason, if you'll let me use the word reason, The reason is that that will increase the entropy, but more appropriately, it's just saying that the random coin flipping of all those molecules, they're just flipping coins. Each one flips a coin, moves left or right. There's no force, if you like. There's no force pushing the molecules over to the side of the room where there's no molecules. All there is coin flips. And the thing is, all the molecules on the left are flipping coins, or on the one side of the room, they're flipping coins, and half of them are getting heads, and it says, step over to the other side. So that's what's happening. It's just a gradient in the number of particles accumulating these coin flips. So Boltzmann formalized this idea in the notion of the entropy, which I show you here, which is to say that there's this macroscopic variable, entropy, which is a state variable. And it reflects a microscopic configuration by saying the entropy is a logarithm of the total number of microscopic states available to the system, modified, or I should say, to give consistent units by the Boltzmann constant, which tells me how the entropy is going to vary in magnitude as a function of this W. So I'm not gonna say too much about it, but if I have a composite system, and this is the part I guess I wanted to comment on, a composite system, then W, which is the number of configurations, is going to be equal to the W of system 1 times the W of system 2. Probably the easiest case to think of would be if I want to know the probability of getting a heads and getting a 3 when I roll a die. These are independent events, and the total number of ways of configuring the system is I have 2 choices for the coin, and I have 6 choices for the die, so that means there's 12 things that could happen. For every heads, there's 6 faces, and then I go to tails, and there's 6 faces again, so there's 12 outcomes. And so the total number of outcomes is the number of outcomes for the coin flip times the number of outcomes for the die roll. And that's what's represented here in my W as number of configurations, which is the product of the number of configurations of the 2 separate subsystems. So what I want to do is I want to use this particular example to make this point. Okay, so what we're going to do is we're going to calculate the condition of chemical equilibrium, and we're going to do that by maximizing the entropy. And probably some of this I'm going to leave to you as an exercise for future calculations in homework. This is just to, in a way, set up the concept. So what I've done here is I've drawn my little universe, which is, as I said before, it's surrounded by a rigid, impermeable, adiabatic wall, and so I can't communicate with that. Sorry, I'm trying to get myself adjusted here. It seems like the computer's a little tilted. And to be concrete, we're going to say that there are L1 or L ligands on one side, and that means there's L tote minus L ligands on the other. The total number of ligands in the 2 boxes is L tote. And so if I put L of them on one side, then that means there must be L tote minus L on the other. I'm going to discretize my system into a lattice. And this is a very convenient dodge that we will adopt over and over again when thinking about statistical mechanics. And so what we're doing is we're saying that there's these omega boxes, and this is going to allow us to do our counting explicitly rather than doing integrals, but there's nothing sacred about it. Now what I want to say is that the total entropy is given by the entropy of the left-hand side plus the entropy of the particles on the right-hand side. And the way that you can think of that is that I can compute the total number of configurations of the L molecules on the left, and that's given approximately by omega to the L power over L factorial. This is my stadium seating analogy that I used earlier in the term, and I will say again now. If we go to the Rose Bowl, there's 60,000 or 90,000 seats or something, and I have a hat that has 30 names in it. It has 60,000 numbers in it, and I have 30 students that are going to sit in the seats. Then what I'm going to do is I'm going to hold out the hat, and I'm going to let you choose your seat number, You choose seat number 600. And you're going to put your number back in the hat, and the next person's going to choose from the same 60,000 numbers. And the reasoning here is that I'm not worried about the same number coming up twice. In principle, I should now have removed the number 600 from the hat, and now there should be 60,000 minus 1 choices for the next person. After that person picks, there should be 60,000 minus 2 choices. But I'm just saying 60,000 minus 1 is the same as 60,000, and so effectively what we're doing is, by writing this way, we're saying every one of the L ligands gets to choose from the entire set of omega sites. So I raise it to the L power because there's omega choices for the first molecule, omega choices for the second molecule, omega choices for the third molecule, and so on. And then I divide by L factorial to eliminate overcounting. This is maybe a technical point. On the right-hand side, I have that there are omega choices to the L tote minus L. So the number of particles is L tote minus L, so it's the same thing. So now what I'm going to do is I basically am going to use the rules of logarithms that tell me I can, take the logarithm of the omega to the L over L factorial. That one gives me this. Note that the first term I have an L log omega. That's just log of omega to the L power, which is the same as L log omega. The minus kb log L factorial, that arises because L factorial is in the denominator, and log A over B is log A minus log B. So I'm exploiting that. And then these two terms are the same thing, but when applied to this second logarithm in the total entropy. So we have our expression for the entropy, and at this point, the last little step is that I'm going to invoke the so-called Stirling approximation. I think I may have talked about this earlier in the term, but just real quickly, in case I didn't, what is log of L factorial? Well, it's log of L. Try and write this cleanly. Times L minus 1 times L minus 2, all the way down to 1. So that's what I mean by log of L factorial. But by the rules of logarithms, this can be rewritten as log of I equals 1 to L of log of I. So that the log of the product ends up being the sum of the logs. And now I'm going to make the approximation that this is the same as the integral from 1 to L of log of x dx. Why would I say that? Well, I would say that, again, I feel like maybe we talked about this earlier in the term, but I forgot. The reason I would say that is because of a graphical interpretation. Of course, you can be more rigorous about this, but so what I'm saying is, if I plot log of L, well, so here at 1, I get 0. At 1, so, and then I start going up the ladder like this. So this is log of L, and then these, I don't know, I'm doing a bad job of making my drawing, but the area under these histograms, this stuff, that's the sum that I'm doing right here. That's the sum. And the integral is the area, so let's see if I can figure out how to do this somehow. The area under this whole thing, that's this. So we're approximating this integral, the sum with this integral, and I know that integral of log x dx is equal to x log x minus x. You can test that. I think you could probably do this by integration by parts. I'm not gonna spend time on it, but so if I do this from 1 to n, then I'm gonna end up with n to 1, and this is approximately equal to n log n minus n. Again, I'm being a little bit fast. I'm being somewhat sloppy, and so if I plug in all of that stuff, what I will get is this expression. right here. And for my purposes, for what I want to say, this is enough. Now, I could take this farther, and probably you will in the homework, but for my purposes, I just want to appeal to the graph that I made earlier. So notice what we've got. We've got the entropy. It's a function of L. L is the number of molecules on one side of the partition, and L tot minus L is the number on the other side of the partition. And so, we're prepared now to write the entropy, or I should say to plot the entropy of the left and the right-hand sides, as shown here, these two entropies. So I'm ready to plot those, and I'm ready to plot the sum. This green curve is what we just calculated. And I could actually take the derivative of the total entropy with respect to L, and what I would find for this case, given that the omega on the two sides is equal, I would find that L over 2 is the choice of L that maximizes the entropy. So half the particles are on each side. But I also would find that there's a condition, which is that the rate of change of the entropy on the left with respect to particle number, it's got to be equal to the rate of change of entropy with respect to particle number on the other side, and that amounts to asserting the equality of the chemical potential. So what have we accomplished here? What we've accomplished is that I've tried to just give you a first acquaintanceship with the definition of entropy a la Boltzmann, and then I've argued that we could remove constraints on these isolated systems and then ask the question of, what happens to the system? Well, we know it equates the pressure on the two sides, it equates the temperature on the two sides, it equates the chemical potential on the two sides. That is the terminal privileged state. It's the entropy maximizing state, and my point is that by virtue of maximizing entropy, we are finding the conditions that we are used to intuitively about equality of temperature and so on. And we could do this for all three of the cases: energy, particle number, and volume. All three of those things can change by virtue of either particles or energy or volume being transferred. So this now serves as the basis for us to launch into a little bit more of a circumspect treatment of this issue of compliance and defiance. When I talk about life as defiance, what I mean, at least for the purposes of the next few vignettes, what I mean is the defiance of this edict, that the system shall evolve in such a way that it shall arrive at the terminal privileged state, which is the entropy maximizing state. For me, I ate food a little while ago, and I am not reaching my maximum entropy state because I'm part of a surrounding reservoir, and together the universe, the rest of the universe and me, together we're increasing our entropy, but I personally am not on this kind of curve, nor are you, because we're defying this edict. So anyway, I'm going to be more concrete about this as we move along, but that's, I think, the essence of what I wanted to say in this first try on compliance.